Let's start with our chapter 2. Okay, the chapter 2 is talking about the visual perception. It's mainly visual perception, how we can see object, and using, of course, using your eyes, how we can recognize object, and based on this information, how we can combine the one you have retrieved from the object into your perception. So visual information is so important because as you can see from this picture of brain, the anatomy of brain, you can see many of part. Okay, around this part of it is our visual information process in our brain. So technical term in cortical structure, we have around 50% of our brain covering the visual perception, and auditory perception is much lower, much smaller than the visual perception. Right. The point about visual perception is, so that is what we have to discuss this week. So I will cover today about this one, and part of tomorrow, and most of the tomorrow is talking about how we can use the contextual information to recognize object. Okay, so main point of visual perception in our textbook, the John Anderson start with agnosia. Okay, this one is particular patient, okay, somebody who has some kind of impaired facility. So talking about two different types of agnosia. One is a perceptive agnosia and the other one is associative agnosia. The idea about visual agnosia is this one. Okay, the people who has a visual agnosia cannot recognize visual object, even though they have a perfect intelligence and perfect sensory memory or sensory perception, which means they can see what we see, but they cannot recognize it. They cannot recognize rectangle as rectangle, they cannot recognize circle as circle. So the idea about these two things is talking about two different visual process. Okay, the last week I mentioned our mind of our information processing is starting with the sensory information process. But in particular, this sensory information has two different types. And that is point about why John Anderson is using these two example of patient to interpret visual perception. Okay, the apperceptive agnosia is this particular thing, is they cannot recognize simple shapes or draw shapes that are shown. And perfectly, they don't know what they are seeing. Okay, so when you show the circle to this patient, they cannot recognize this one as a patient, but they can see it, but they don't know exactly how it works, how it recognizes. That is very early process problem. Second problem is they can recognize the shape, but they cannot associate with what they have seen and object. Idea is this one. Associative agnosia is this kind of thing. They can copy this picture into in here. Okay, when they see this one, they can copy it, but they don't know what it is. Okay? We know exactly this one is anchor, but they couldn't recognize this one as an anchor. But they copy it. They can draw it, but they couldn't recognize this one is as it is. Okay? So from this one, we understand two things. Okay? Many of the psychologists understand, perhaps, that is assumption, that is theory, right? It's a theory. We may have two different stages in our visual perception. In the first phase, we extract the information. We extract the feature. Okay? So when you see this one, you're trying to extract the feature of this object. That could be rectangle, black color, right? So that things can be perceived in a first phase. Okay? So if this one is not working, we can call this patient is a perceptive agnosia. The second phase, when they receive the feature or when they identify the feature of object, now it's time to link what they have achieved from their visual scene, which means features should be combined with what you already have in your brain. Okay? The idea is this one. So, okay, this one is bottle. You already know it. But if you want to recognize this one as a bottle, you have to have some kind of template. Well, we don't know exactly, but something in your memory, something in your brain. So when you recognize this one, okay, this one has cylinder type with something inside. So we made this one can be matched with the bottle, right? If you don't have any bottle in your brain, you can't recognize this one as a bottle. Like a 1 year old, the infant, they may not recognize this one as a bottle because they don't have any experience or any knowledge about this bottle. We don't know exactly how this process happens or what is exactly what happens in neurophysically in our brain, but our scientists trying to interpret our visual perception has two different phases. One is early phase to retrieve the feature, and the second phase is these features matched with something in our brain, and then we recognize this one as an object. Okay, right. So that is basic stuff. So and then I have some video clip in here. This one is a pencil sorting machine vision system. So this machine can detect which one is defective item, which one is not, and which one goes into the colored pencil, which one should go into the black pencil. So using a camera in here, they are taking the pictures of this each of item. So if something wrong, they can just push it away. Okay. I also uploaded this video clip on our course webpage, so you can have a look. The idea about this machine vision system is exactly copy what we are doing in our normal life. We have two phases in visual system, right? One is early phase and second one is matching phase, right? The extracting the feature, and the second one is matching algorithm. So this machine vision system exactly copy what we do. So first time when they taking a camera, take a snapshot of each of the product, and then they retrieve the features to be seen as a defective item. Okay, they already define an algorithm. Okay, this part, if something wrong in this part, we can call this one is defective item or something else. So that they are just extracting the feature from the pencil and then matching it our artificial intelligence algorithm. Okay, many of the computer system or vision system or the works done by the computer scientists is looking for our human, right? They just copy what we're doing. So that's why in the later chapter, the end of the chapter 2 is talking about the feature map. I hope you read the textbook already. So feature map, and then many of the modeling algorithm to use how we can recognize object, how we can import this understanding into the machine vision or system development. That's what we industry engineers or computer scientists have to work on to understand this part and imply into some development. That's what I want to show this example to you. This one is something we mentioned in the last week, but this example can also repeat what we just heard from this John Anderson textbook. This one is simply dot envelopes, right? So when you see this picture, you retrieve many of the features in here. But later on, you can recognize this one as Dalmatian, right? The dog. So it's kind of, when we retrieve some of the feature itself is not much important at this time, but sometime later, you can interpret these blobs and dots into the dog. Which means, what you see is not what is out there. Computer cannot do it, machine cannot do these kinds of perception. Only human can do it because we have something unknown in our brain. So that's why the psychologists look through why this happened, what triggers this whole process. So, and then, like me, is to using this understanding into the system development or information design. That's why we have to learn the cognitive psychology in industrial engineering. And another one, end of the chapter 2, is talking about the context, which is a really beautiful research topic. So nobody has done much yet about how the context can work with our visual perception. So one of the examples is this one. What is this? B? It depends on, if I write down in here, many of people will say this one is 13. But if I write down some of the different things, they will see this one is B. Even though you can retrieve the feature of this one, it doesn't itself perfect, right? It doesn't itself sufficient. So sometimes human need or human use the context or peripheral information to recognize the main information, the target information. So that's why end of the chapter 2 is talking about context in perception. Another one is, I can't draw much well. So one of the thing is, have you seen red banana? Red banana? Red colored. Is there anyone who likes bananas every banana is yellow? But if something happens, if you just propose or if you just present information of the banana with the red colors, it is really hard to recognize it. Because you already filter out some of the information, okay? Even though that is real banana, red colored bananas, you can just filter out this information because I never seen red banana in your lifetime. That's why you just filtered out. So let's imagine that. So everyone, every operator or every end user, like mobile phone user or system users, they already have some kind of expectation, such as, okay, start menu on the left bottom, because many of the Windows system, but Apple has a start button on the left top. It's not actual start button, but they can access it. So depending on who you are or depending on what experience you have, maybe you have a different expectation to see. See? That's why when you develop the information or design the information, think about the end user. Generally human being, and also think about end user. So that's why, so this visual information like this one can be interpreted in a certain different ways depending on your context or depending on where you focus. Okay, the point is this one. So now is go into the visual system, anatomy of the visual system. Look carefully this video clip.
In order for one to see, a light source is required. Without light, everything is black. The light emits particles called photons, which bounce off solid objects in all directions before eventually reaching the eye. In order to see well, the tissue that they go through must be transparent. First, the cornea, located at the front of the eye.
This one is cornea.
Then, the crystalline lens behind.
That is lens.
Then, the vitreous body in the middle of the eye.
Retina.
Finally, they reach the retina, the eye's photographic plate, stopping at the retinal pigment epithelium, where they set off nerve pulses.
That is ganglion cell.
These pulses are directed towards the optic nerve. and then the optic pathways, before arriving at the occipital brain where the image is formed. This process is what enables us to take in the world around us.
Okay, that is basic anatomy of our human eyes. Education, okay, this one. That is more detailed information of how our vision system is working. So retina in the back of our eye, the most important part of visual perception. Cornea is not much for us. That is optical nerve. The interesting part of this brain, which I will explain later on, is we have two eyes. Because of the two eyes, we can have 3D perception. Okay? And then this purple color and gray color, bluish colors has a different part of our visual nerve. As you can see, each eye is connected with the two parts, right? Two visual parts. And then as you can see, this right purple colors is connected to the right hemisphere. Okay, this part. Okay, and the bluish and gray color is the left part of our brain, which means this left side, this bluish color, is covered the right side of the object. Okay, this brain, okay, is covered, okay, this angle, and this one has this angle. So I will explain later. So we have separate part of, okay, the visual system. Okay, that's how it works. And then we have to look into a little bit detail about how our visual system is working. So basically this one is spectrum, the light spectrum. Only we can see it has a visual spectrum area. Okay, so visual spectrum area. So you have to see this part. So red colors is covered by, around the visual angle is 700 nanometers, and violet has a 400 nanometers. So this part is ultraviolet and this part is infrared, which we cannot see it. Only we can see is this visual spectrum. This one is really important because our color vision is only limited with between this around 400 nanometers and 750 nanometers. More than that, we can't see it. Okay? So that is the anatomy of our lens. Point is, phobia is interesting part. When you have to focus on particular object, all the information coming through your eyes can be around in this phobia. So when you need to focus, okay, the light must be stay in the phobia. Okay, and then of course, and then the optical nerve is carried through all the information. And the second part is retina is also important. Most of the retina has a constant rod. Our black and white perception, the light perception, as well as color perception. Okay, still not used it. Retina is really important part. Okay, thin light sensitive membrane located in the back of the eyes, and they have two sensory receptor for vision system. Okay, I will explain rod. Okay, so this one is ganglion cell. So retina has many cones and rod is for color, black and white brightness perception, and cones for color perception. Okay, this one is part of our nerve cell. So in our textbook, it's talking about the ganglion cell, how this one is coded or decoded, plus a minus sign. I will explain step by step. This one is your part of study. Okay. One more video clip I had prepared for your understanding of rod and cone. In particular, cones are very important things we have to memorize for your first essay question.
Each of your eyes has over 3 million photoreceptors called rods and cones. These receptors convert light into electrochemical signals that travel through the optic nerve and into the brain. Here, these signals trigger a neurological process scientists call the connection that happens.
That is my favorite, Simpson. The small rectangle one is without cones, we can see only black and white. So we have 3 cones: red cone, blue cone, and green cone. So that's why RGB colors comes from this cone structure. Okay, so I uploaded this video clip right now, course webpage. So if you're interested, you can have a look a little bit more. But the point is, okay, this one. Okay, that is your self-study. Okay, self-study. Oh, this one. Okay. So cone is very short and thick pointed sensory receptors of the eyes and color perception. Then most of cones are color vision and acuity, the accurate perception. If you need accurate perception, you need the cones. But rod, in contrast, they have peripheral information perception and night vision. Interesting part of this one is I'm not sure about whether this kind of research has been done or not, but elderly people might have some kind of night vision issue, right? They can't drive in night, and my daddy can't do much well. That's why you may need to study about whether elderly people might have some kind of impairment on their rod rather than cones. I haven't researched on that yet, but it could be a good research topic. So if you understand the mechanism, say, okay, elderly people, they have a lack of node or something problem in rod, we can develop some kind of medicine or cognitive rehabilitation skill, okay, training. Okay, so that is the thing. Okay, next part, which I prepared for you, is this one. I mentioned that cone is color perception, and as you can see, we have 3 types of cone. Okay, red cone, green cone, and blue cone. Each of the cone, in particular red cone, covering this red color area. So around 400 nanometers to 700 nanometers. Of course, this major part is this area. Okay, the green cone has this one. And the wavelengths of the light, they cover around in here, and blue cones covering this part. One interesting question from this picture, okay, this one is a low, medium, short, medium, large wavelengths, okay? Okay, so that is, we can just interchangeable. This one is red cone, green cone, and blue cone, okay? Their working area. Right, interesting question in here is we have 3 cones, okay? 3 types of cone. The first question is, why green and red is combined? Much of them overlapped. Why the area is overlapped? Why we have a distinctively different wavelengths like what we use in computing system in color production RGB system. In color production in computer, we have exactly 3 the distinctive the area. R is 0 to 255, G as well, and B as well, 0 to 255, right? Okay. Why we don't have this kind of scheme? Human eyes has a pretty much overlapped area in medium and large wavelengths detection. That is first question. Any thought or any implication? Why we overlapped much? Why the blue color is pretty much skewed in the left, more high? The short wavelengths. Any implication? That is first question. And second question is, if we have one of the cones are totally impaired or damaged, do you think that our color perception is exactly the same with what we see now? That is second question. Perhaps if the green cone is totally malfunctioned, can we see the color as it is? No? 2 questions. Nobody knows yet because we can test it. We can have some kind of computational model with this one. Okay, so that we can have a better understanding that, and with some kind of the biological experiment with the mouse, it can, but I need your imagination. That is your first essay. So, before we going further, okay, the second question is, I made some example why the blue color has that. Is this one. When you see many of the web page design like this one, okay, this one is blue background and red color. This one is the other way around, right? So this one in particular is quite difficult to read it. The reason is we can interpret that the blue color, blue cone is much isolated, right? So that means we have quite a small number of cones only can cover this bluish color. Okay? That's why if you have too many blue colors in your information design, it might be a problem. In particular, the elderly people. As well as if you have many color like blue with something red colored one, you can have much fatigue, tired. The eye is much tired. I'm not saying you can't use the blue on information design. Blue means something emotional color. And most of the male student likes the blue colors because that gives us some calming, okay, as well as cooling feeling. So that's why many of websites use a blue color. However, what I'm saying is when they have to look through or they have to read as many as text on the web screen, right, the blue color background is not much good for reading perspective. So I'm just changing some of the things with the green and red cone. So we have some kind of, how can I say, compromise. Supporting each other. We have 2 different types of cone can cover most of the range in here. So if you're using many greenish and many reddish colors, like this one, it might be usable information design in terms of readability or in terms of the cone's anatomy. Okay, that is linked to your first essay. I decided we are not taking midterm exam. Okay, we don't have any midterm exam. So you have first essay because you are my hostage. You can't drop out this paper anymore. Okay, you are my hostage, so you have to finish this course until end of this year. Okay, so I made something trick you. So this information in our course web page, right? My question is, we have red cone, blue cone, and green cone. Question is, if the one of cone is not working, what happens? Same perception? There is no right answer. Don't search on the web, but you have to look through your textbook plus many of the web information. Do not copy and paste. Plagiarism is not good. I mentioned that. So that's why you have to use your imagination, but of course must be reasonable or sensible answer. Don't say, I don't think so. Okay, you normally, when I ask these kinds of questions, they say, I don't think so. I don't know what it means. But you have to interpret. Very short essay, less than 500 words, or 1 or 2 pages, of course in English. You are my hostage. In 2 weeks' time, that is 5%. Either email to me, or you can upload your Word or PPT, not PPT, Word file or HWP file or something else on our course web page. Either or me. Interesting question. I want to see your imagination. So, and then your interpretive power. Look at the textbook, many of the course web page, the web pages about visual perception. And third one you may look into is some of the video clips, which I include in our course web page. So you can make an answer. Questions? 토끼. whatever. 예.
교수님, 이건 제가 좀 예전부터 궁금했던 건데요. 저희가 그 흑백 영화나 오래된 흑백 영화나 만화책 같은 경우에도 그 흑백으로 나오잖아요. 고급 말고 그냥 일반적인 만화책은요. 근데 저희가 처음에 그런 것을 볼 때는 흑백이라서 칙칙하다 하고 보지만 한참 열중해서 거기에 빠져들다 보면 어느새 그게 아주 생생하게
그렇죠. 그럴 수 있어요.
그래서 이게 단순히 그냥 저희의 상상에 의한 것인지 아니면 저희가 오늘 배운 이런 인지과 관련이 있는지.
Okay. So what he asked me is about when you're just reading black and white cartoon movie stuff, cartoon books. So, in the beginning phase, we just see this one is black and white color, but sometimes later we just imagine that this one is some kind of vivid color thing or color perception, something. So whether his question is whether this one is imaginary feeling or we can use our understanding from this visual perception to interpret these kinds of symptoms. Answer is, I don't know, but I probably say the first one. So when you look into the many of the visual perception and audio perception, our memory is working to perceive the object. So in that case, so even though we see this one is black and white, but we're just adding up our previous information to add on this particular product. That's why we believe this one is color, imagine this one is color, but nobody has done this experiment before. So you made theory. You can make a theory. It could be useful for academic-wise and practical-wise, industry-wise. But I think the first one, okay? So our imagination, okay, that's a good question. So this one is first essay. 5%, you're my hostage. Okay, you can't drop out anymore. Okay. Okay, so this one is your self-study, and this one is a ganglion cell. Okay, I mentioned that ganglion cell in the retina, the specialized neuron that connect to the bipolar cell. Okay, so image, perhaps. Okay. Okay, this one is ganglion cell. Okay. So this one is kind of receptor of the light, proton. So that comes through, the light comes through in here, so we have cones and rod. Okay, cone looks like this way, the rod is rod. And then coming through this one, and the ganglion cell is encoding the information from the visual spectrum. Okay. Okay. Your self-study. Okay, this one is what we. Okay, so. Okay, our eyes. This one is part of retina, right? Both of them, and one is bluish colors, and the other one is reddish color, right? Okay, this reddish color, the right side of your eyes. Right side of your eyes connected to your right hemisphere. Okay, and the left side of your eyes is covered by left hemisphere. Okay, and then of course this angle is this part. So left part of your eyes is covering the right side of your world. Okay, left part is right side, right part is left side. Okay, so that is how we see the world. Because of the small discrepancy between the left and right perception, we can see 3D images. That's why 3D TV or 3D lens or the goggle is working like that. Exactly like this one, parallax, a slightly different angle. Okay, so that's why this one is what we have mentioned in the textbook as a particularly important thought. And the most of the part is your self-study. Okay. Okay. Okay, this one is our textbook images, same with the previous one. Okay, so second part of the topic is receptor field, ganglion cell. Okay, so in our textbook, it's talking about ganglion cell as on-off cell and off-on cell. So the interesting question of psychologists is when the information is coming through to your eyes and strike on your retina, how this one is encoded in your brain. So the main component to process this part is ganglion cell. In particular, ganglion cell, many people believe they might have two different cells. One is on-off cells and the other one is off-on cells. We can't see the eyes of human eyes. We just identify this information from mouse. Okay, not Mickey Mouse. Okay, real mouse. Okay, not rat. Okay. So this one is on-off cell. This one is off-on cell. Okay, the point is, the understanding is, if we have these two different types of cell, okay, on-off cell in particular in this one, when the light hit this cell, when they are more close to the center, this one is activated. Technical term is firing. Okay, when the light comes in, okay, some of the light has something is, it's black outside, and some light has this one. So when this one is coming through this ganglion cell, okay, this one this one is firing, and the rest of the part is not firing. This one is called on-off cell. The ganglion cell has this one. Another one is this one. That is reverse way. When they hit the light, in this cell, the middle is not firing and outside is firing. Combination with this one, we can have a bar detector and edge detector. Okay, so actually there is 4 different cells in our ganglion cell. One is on-off cell, off-on cell, bar detector, and edge detector. This one is not much important for your studies, but I'm saying is we assume that we have 4 different the cells in our ganglion. Nobody's seen this one. That is not a real thing. We just interpret it. Okay? So how people can detect a color or how people detect a light. Say, we just using these kinds of assumptions like atomic structure. We cannot see the atomic structure. Well, now we can see some part of it. But I mean, basically we assume that atomic structure to understand the physical world, right? So like this one in psychology, we just assume that particular cell in ganglion works like this way, on-off, off-on, and then this one goes into the edge detector, like this one is edge detector and bar detector. Okay, combination of on and off, so this one, this part is activated so that we can see the bar, okay, line, okay, using this, this one is bar, this one is edge detector. So edge is normally black color, right? The other one is white color, right? So using these kinds of different cells in our ganglion, so we can understand, okay, the light vision thing. I don't need the detail of this one. Just that this one is working in our eye structure. So edge detector is respond positively to the light on one side of the line, and bar detector is about the bar detection. That is probably from the theory of our reception. Okay, the last part of visual information processing is a feature map. That is what I explained it. That is on-off cells, or when the on-off cell is combined, we can make a bar detector. Like combined with this one, we can have another bar detector, also edge detector. That is assumption of our visual perception. The feature map is this one. This one is probably much arguable. So this one is not exactly, I mean, many of the experimental outcomes support our retina or our eye structure might have this feature map. Very, how can I say, it's very ambitious approach. So it's pretty much computational approach. Okay, say if our eyes has this kind of 2-dimensional structure, actually 3-dimensional structure. Okay, so each of the part is covering a particular feature of the object. But this one is very tiny. Okay, the eye has heaps of this one. Okay, heaps of this featuring. So each column, okay, this column is detecting the straight line. Okay, and then this one is horizontal line. Probably our eyes, I said probably our eye has heaps of these columns, imaginary columns. So this imaginary column is working to detect the shape of object. Idea is that, but nobody knows yet. This one is part of interpretation. This one is working in many situations, so that's why we believe that that has interpretive power. Okay, so this one is one of the example of feature map. So in the end of the chapter 2 is talking about the feature analysis to recognize letters, right? Similar with this one. Okay, so that is feature map. So I hope one of you make this feature map. Okay, this one is very important for our vision system. So if you have a nice feature map like this one, you can make better vision system, machine vision system. So machine vision is really important in applications such as we have seen the pencil sorting machine. but that is tiny application, industrial application. Big application is the food poisoning. Okay, every food industry has a concern about whether this food has a food poisoning or not. Okay, so in particular EMAT or the other place, they have the scanning every product, right? So nowadays we only can see the manufacturing day, right? So based on this information, okay, that is 2 days ago it made, so we can believe this one, yeah, it's not much rotten. But when you have a nice vision system I saw once in New Zealand, they have industry, the cattle, the meat industry, right? So every meat must be separated into high quality one and low quality one. High quality one is consumed normally in Japan and New Zealand. The low quality one is exported to other countries, including Korea. Okay? So when they're coming through the conveyor belt, they have a vision system up there so that they are automatically filter out, okay, to sort out the best quality meat and low quality meat. See, with only color perception. So nobody can, every employees, the workers, the labor cannot recognize which one is good, which one is bad. But when you're using the machine system, in particular, the feature map, which you developed one day, so you can apply your feature map into many of the industrial applications. The food industry as well. So the high quality one, they're using only color, okay? They do not destructive inspection. They're using only color one. An example. So that's why we have this understanding to apply in industrial application. And our textbook is talking about something else, about depth and surface, more about 3D images. Okay, so the John Anderson mentioned about 3 different types of cues we can recognize the depths. We have 3D, okay? We have 3D vision. Computer cannot have 3D vision. We have. That's why how I recognize 3D. One of the examples is texture gradient. Okay, say this one. So when you have this information, right, and this one, that is more sparse, big gaps between them, and this one is quite collapsed, okay, close each other. So when you see this part, that is farther from us. See, when I'm in here, I can see big face, big face is in here, but the nice face behind is very tiny and small. Okay, so that's why in the same angle, okay, I can see big face, the big space between the object. Or when you see the back, there is only small gap. So using these kinds of information, we perceive, human perceive the depths that is further from me. Likewise, this one. The more implication, still not get used. Okay, this one is kind of 3D introspection one. Say this one is pretty much tiny, the lines, so that is farther from us. This one is quite narrow and detailed, right? So when you see this part, so that is close to us. Of course, the relative size is different. Okay, so the truck small, this one is bigger. Likewise, that is called the texture gradient. And second cues for the depths is stereopsis. So many 3D movies using this one. So as I said, our eyes slightly apart between them, right? It's not the same thing. We have slightly apart, right? Left and right. And then your visual angle slightly different. Okay, that's why I can recognize you in 3D. So that is called the stereopsis. So many 3D, the goggles using these kinds of understanding for their industrial application. And motion parallax is this one. So in this big picture, right, if something is moving around, you can easily detect. Okay, that looks faster around in here. But when they are moving in the same speed with this one, they cannot recognize much of their speed because the distance, what we actually see, is very narrow. Exactly the same thing. When you look further, something is very slow, like an aeroplane on the top. It looks very slow, isn't it? But actually very close, very fast, right? Sometimes. So that is motion parallax. As more distance point move, they will move more slowly across the retina than closer point. So these three visual perception is the things we have to look into the depth Q. Okay, so am I right? Okay. This one is something I did with some robot interface design in 2005, 2006. I had made some couple of experiments about the map design for controlling the robot. Okay, and very similar with our interpretation in textbook saying 2.5D map. Okay, 2.5D map is this one. It's not 2D map. If you look at this particular object, that is bookcase and cabinet, it shows some of the height. So what I did is escalating the object a little bit further. So it looks like it's not 3D because we have from the top, so that is called the 2.5D. 2D is only plain information, right? 2.5D is slightly escalating the length a little bit higher. But 3D is different one. 3D is you have many of the navigation system as 3D images. But 3D on navigation to controlling the robot is really hard. The reason is the distance is not much recognizable. 2D map is very good for locating particular information, particular target destination. But 3D is really hard. When you have a 3D navigation, you can't exactly pinpoint the particular destination, but 2D map, you can do it. But 2D map doesn't have any real images like 3D. That's why in a compromise between 2D and 3Ds, our textbooks say 2.5D, and this one is my experiment for robot control. So what we made is the tablet PC is a similar size with the iPad. So I made the iPad and then 2D map of these particular rooms. The robot is around in here, and then I have to order this robot to move into particular target places. Okay? We can do verbal commanding, but that doesn't clear. So that I use the iPad to pinpoint particular location on my map, and then robot can go there. Right? So in that case, what types of map is better for human understanding? Because human is operator. Okay? That's why we use the 2.5D, 3D, and 2D. So we controlled this experiment, identified this one is better map design. That is done with American University, and I made this map. So we have a robot from KAIST, and I designed the map. And some of the experiments done in New Zealand and Australia and Korea as well. Okay, so this one is similar with our topic in 2.5D in our textbook. Yes, Gestalt now is object perception. One more video clip. Gestalt is German psychology, so I just download something about Gestalt.
Guten Tag, I'm Hans Wertheimer, and I am here. Welcome to the Gestalt School of Learning.
The Gestalt School of Learning is based on how we as animals take individual parts of objects, situations, and problems, and use prior knowledge and insight to see them as a whole. This is very difficult to understand, so we have made videos for you.
I mentioned about 5 Gestalt laws.
Where we see all these component parts is categorized into the Gestalt laws of perception. Here we have a countdown of the top 5. Are you ready?
No.
And number 5 is the law of finance, or the law of figure in English. This is best explained like many of these laws by looking at some examples. The law refers to the way that we as analysts see things in the simplest form. Instead of seeing the figure here as a series of complex shapes, we see it as 5 simple circles. Like here, we do not see this complex figure as like an ice cream cone with a couple of shapes on top. We see the figure like this in our heads. Unless you are certain PhD student or something, then maybe you see the ice cream cone.
In at number 4, the principle of figure ground. This principle is where the two figures overlapping. The larger of the two is perceived as the background. However, when looking here, we can change between seeing two people looking at each other and a beautiful vase. My dear Muta would have liked this vase. Anyway, it is not possible for us to see the vase and the faces at the same time. Here are some real-life examples of the law. The famous Mark sign looks like a smiling face or in profile and looking straight ahead. And the other one looks like 2 cats or something.
In at number 3, law of closure. This example is a tendency to close simple figures, therefore filling in missing parts to make a whole. If you look at this example here, I bet you see a triangle, don't you? And this figure is pretty cool too. Even though you're only looking at triangular shapes, you see a big spiky sphere, like a big spiky planet or something. A real life example of this is the EVM logo. You are just looking at straight horizontal lines. However, your brain sees the letters E, B, M.
In at number 2, the law of similarity. This principle is that objects are seen to belong together due to their similar shape, size, and color. For example, we see these circles as alternate lines on the page due to the contrast in the colors. And we see the circles and triangles in a similar fashion due to their different shapes. It is very hard to see these images in vertical lines. Give it a try. A real-life example of this in computer interfacing, like on this iPhone screen. The apps all have similar shapes and therefore are put together in one's mind.
And now, the moment you have all been waiting for. At number 1, the law of proximity. This is the principle that objects which are closer to each other will be seen as belonging together. This is perfectly demonstrated by the little dots. You see the large group of dots to the left as one group, but when they are split into pairs of lines, your mind will see them as 3 groups. The most common use of this law in your everyday life would be in the computer keyboard. In fact, many of these laws are used for human-computer interfacing. Your mind will group together the keys which are at closer proximity. For example, splitting the letters here from the numbers here.
We hope this has been informative.
Okay, that's about the Gestalt understanding. Okay, so this was one of the branch of the psychology of visual perception. So Gestalt psychologist is looking to a somewhat different angle, somewhat different approach, such as they only concern about the mental structure. So how our mental structure can recognize object. So that's why when we see the 5 principles, actually the 9 principle is proposed by the Gestalt psychologist, is looking for how the information is structured. So this one can be automatically recognized our brain. So that is another approach in visual perception. So what we had done with John Anderson about the feature map, also the anatomy things, cones and rod, that is another branch about visual perception. Because we don't know exactly which one is right. Everything makes sense. Okay, this one makes sense, and this one makes sense. And another approach is called Gibson's affordance concept. Gibson, which we'll see in week 5, Gibson see the old object perception is not like a destructive or divide and conquer approach. The Gibson proposed that our visual perception is one shot, one kill. Okay? Say, when you look at this one, okay, so previous interpretation with John Anderson, with many experiment, one is we have extracting the feature, right? Okay? But Gestalt psychologists, okay, we don't have any structuring, but when we have this kind of line information, okay, they can have a similarity on that sort of thing is our visual perception. And Gibson's say, okay, we are not simply perceive this one as a bottle. We recognize this one as a drinkable, not throwable. Okay, when you look at any object like this one, so computer cannot recognize this one is a chair because we have thousand different types of chair, isn't it? So if you want to make computer recognize all the chair in the world, your programming code is enormous, right? You can't make it actually, in practical wise. But we human beings see every chair is chair, right? How that is happens. So that's what Gibson say. Simply don't look at the object featuring. The chair is sittable. Okay, we perceive this one as not an object, including action. Okay, everything has an action. This one is, water is drinkable. You can't throw it away. But when you perceive this one is writable. Okay, it's not, that is pencil or ballpoint pen, but Gibson proposed that this one is writable. Okay? So people can recognize action as well. That is what Gibson's proposed as affordance. So many of the affordance is being used in information design, say the button, Windows button, like this one. That looks like button, isn't it? When you look at the button, what do you want to do? Click. Isn't it? Button, click. Label, don't click. Label is label, right? If you make this design, it looks like a label, nobody wants to click it because that doesn't give you an action. Isn't it? That's what Gibson's proposed it. That is another angle for the visual perception. We have many different theories. Okay, Gestalt, Gibson's affordance, and our textbook approach, pretty much anatomical approach, which one might be useful too. Basically, this one is many theory can be used. Okay, one more things I can, and then stop the lecturing. Okay, this part. Okay, this one is example, which we in the textbook say similarity, the symmetry, closure, and continuity. And this Gestalt understanding is also applicable for object perception, which will be covered tomorrow.